In this lecture, we will be covering the topic of graphing polar equations. So, recall that one of the issues with polar coordinates is that polar representations of points in the xy plane are not unique. As a result, we define the graph of a polar equation as the set of all points, P, such that each P has some polar coordinate representation satisfying the equation. This means all of the polar coordinate representations for the point don't have to satisfy the equation. You just need at least one. And recall that this comes from the idea that if you have your point r theta in the xy plane, so we define it by this line segment connecting the point P to the pole, which is the origin, you can do things like add multiples of 2 pi to the theta, and that rotates you back to the original point. You can also account for negative r, which takes the point and reflects it through the origin. So because of this, we have many ways, infinitely many ways, to represent any given point in the xy plane in polar coordinates. We also discussed in the previous lecture that we look for symmetries when we have a polar equation. And the symmetries help us in the graphing process because it allows us, if we detect a symmetry, to copy things over, to reflect about an axis. So recall, we had said if you have a point r theta in the xy plane, and you want to try to detect x-axis symmetry, then that amounted to reflecting our point about the x-axis and noting that this line segment connecting the pole, the origin, to our point, to our reflection about the x-axis can be written with the same length r, but the difference comes in the theta. So we saw that this was our theta for our original point, but for our new point we can use minus theta. And we saw that if this r negative theta and r theta both satisfied the polar equation, the graph of that equation was symmetric about the x-axis, which means that anything we draw up here, we reflect down below. And we made similar arguments for y-axis and origin symmetry. So this is a good first step because it saves you work. So for example, let's look at r equals 1 minus cosine of theta and check for symmetries. So first we check for x-axis symmetry. So we want to know if we replace r and theta with their counterparts in this point, do we recover the original equation? Let's check. So we have r, and we have 1 minus cosine of minus theta. But recall that cosine of theta is an even function. So we get r 1 minus cosine of theta. Again, because cosine is even. And notice we have, in fact, recovered the original equation. So we do have x-axis symmetry. How about y-axis symmetry? Well, we could check r and 1 minus cosine of pi minus theta. We can use our identity that cosine of a minus b is equal to cosine of a times cosine of b plus sine of a times sine of b, where pi plays the role of a and theta plays the role of b. And we get 1 minus the quantity cosine of pi times cosine of theta plus sine of pi times sine of theta. We know cosine of pi is minus 1, sine of pi is 0, so this becomes 1 minus a minus, or plus, cosine of theta. And we see that we do not recover the equation. We would have r on the left and 1 plus cosine of theta on the right. So we do not conclude, or we cannot conclude, y-axis symmetry. And it's important to say it this way because at this stage, such symmetry actually could be there. We just didn't pick up on it if it is there. And recall, because every point has infinitely many characterizations in polar, we just checked this one to try and pick up y-axis symmetry. There are many others we can use to check for y-axis symmetry. So again, we can't conclude it's not there. We can only conclude that we didn't detect it. And we can check for origin symmetry. So we're checking the point minus r theta. And again, recall where that comes from. If this is r theta, minus r theta is its reflection through the origin. So we're checking minus r and 1 minus cosine of theta. Well, we can see we're not recovering the original equation here. 1 minus cosine theta has to equal r for the equation to be satisfied. So we cannot conclude origin symmetry. And also, you don't have to check for each of these in every example. Oftentimes, you can look at the example, look at the equation, and get a sense whether or not you might be able to pick up one or even two of these symmetries. But the rule is, if you pick up at least one symmetry, it's going to help you substantially in the graphing process. So here, we know that we have x-axis symmetry. So anything that we graph, we will also reflect about the x-axis. So how do we graph these things? Well, one way that we looked at in an earlier lecture when we introduced the idea of polar equations was simply to just start plotting points. And that is a way you can do it on a computer or a calculator. But when you're actually graphing these things by hand, that's not typically an effective way to graph polar coordinates. And the way one really powerful technique for doing this, the way we often default to graphing these things, is to think in different spaces. And that's the important thing to recognize in this slide, is that these are different spaces. We think about our polar equation in the r theta plane, treating r and theta like rectangular coordinates. So for this step on the left, you take your equation in polar and pretend like you've never even heard of polar coordinates. Work with them like they are regular old rectangular coordinates. So we graph here, treating r, or theta and r, like x and y. Then we look at that and we use the information there to translate. Translate/interpret. And over here, we interpret the information from this r theta space to the graph of the polar equation in the xy plane. So you can think of this as, over here, you get the story of how r and theta relate graphically when you treat r and theta like they were regular old rectangular coordinates, and then you use that story to translate and interpret it to see how the graph appears when you interpret r and theta as polar coordinates. It may sound a little strange, but it is well illustrated with an example. So let's think about the example that we're working on in this lecture, r equals 1 minus cosine of theta. And here we're going to work in the r theta plane. And again, we're going to pretend or treat r and theta like rectangular coordinates. So, what does the graph of r equals 1 minus cosine of theta look like? Well, let's draw a few graphs to work our way up to it. We know that cosine of theta would look like this. Well, we need to deal with minus cosine of theta, which means we reflect this picture here about the x-axis. So r equals negative cosine of theta would appear as such. And if we want to add 1, we shift it up by 1. And we can think about what these intercepts will look like, but why don't we go ahead and graph it here? So if we shift this up by 1, we know cosine has a range of negative 1 to 1. So if we add 1, it will have a range of 0 to 2. So say this is our 1, and here's 2. So we simply take this graph and shift it up 2 units. And so we have something that looks like this. And again, this is treating r and theta just like rectangular coordinates. And we can label some things here. So we know that, right, this is all based on, we can base everything on this original cosine graph. So we know that cosine had a root here at pi over 2. So we know it's actually, this graph actually hits 1 at pi over 2, and also at minus pi over 2. And we know cosine of theta hit a minus 1 at theta equals pi, which translates to this peak and this peak at pi. And we hit 1 again here at 3 pi over 2, as well as here at minus 3 pi over 2. And we hit 0 here at 2 pi and minus 2 pi. So this is the way we would graph this as if we were graphing y equals 1 minus cosine of x. Nothing more. And so what we've done in this exercise here was really nothing more than what we would have learned in a trigonometry or a pre-calculus class. How do you actually graph this? But now we go to the phase where we interpret it. So this is this same picture. And we have values. We have pi, 2 pi, minus pi, minus 2 pi, minus 3 pi over 2, minus pi over 2. So we're just relabeling the way we had it on the previous page. We now want to interpret this. We want to think about what story we can get from this relationship between r and theta and use that to interpret what the graph should look like over on this side when we work in the xy plane, thinking of r and theta as polar coordinates. So let's start with thinking about this region here. So here we have theta ranging between 0 and pi over 2. And let's think about what it means as we increase theta, right? This is the theta axis here. As we increase theta from 0 to pi over 2, r starts at 0 and increases to 1. So that's just reading this plot. But what does it mean to increase theta from 0 to pi over 2 over here? Well, it means we sweep out this range here for theta, the first quadrant. And this is telling us that as we sweep out that first quadrant, when we start out at theta equals 0, we are at distance 0 from the origin. That's what r represents. And then as theta increases from 0 to pi over 2, the r is increasing. The point is getting further and further away from the origin until once theta is equal to pi over 2, it's actually a distance of 1 from the origin. So we start out here at 0, and then as we rotate, we're from theta going from 0 to pi over 2, we're getting further and further away from the origin until we hit that maximum of 1. And so this highlighted area, the story that this tells, is this piece here. So that is this piece here. What about the next region? We have pi over 2 to pi. So pi over 2 to pi, that's our second quadrant. So if we rotate, if we increase theta from pi over 2 to pi, that is rotating through the second quadrant. What's the story that this tells? This tells us that, and maybe we can write it out so that we can have an idea explicitly of what we're doing here. The story told by this piece of the graph is that as theta moves, or increases, we should say, from pi over 2 to pi, r, or we can interpret r, the graph's distance from the origin increases from 1 to 2. So as we do this sweeping out of the second quadrant, the point has to be getting further and further away from the origin until it hits this maximum distance of 2 at the point in xy coordinates, negative 2, 0. So as we rotate through that second quadrant, we're getting further and further away until we get that far at 2. And so this is that second highlighted region. Now, note, don't forget, what did we detect early? We detected x-axis symmetry. So we can utilize that x-axis symmetry to reflect this entire piece down about the x-axis. And in doing so, we get this mirror image that will appear like this. Now note, we could have continued. We could have looked at this region for theta going from pi to 3 pi over 2. That would sweep out the third quadrant. And we would have said r, the distance from the origin, fell from 2 down to 1. And we could have drawn this. Then we could have said, sweeping out theta from 3 pi over 2 to 2 pi. That's the fourth quadrant. And r would fall from 1 down to 0. And we still would have gotten the same graph. But the issue is that we are able to save ourselves the work by exploiting this x-axis symmetry. So the symmetry really does pay off if you detect it, especially for polar graphs that get more complicated than this. And this is really a classic way to graph in polar. It's also possible that with some examples, you may have other patterns that you don't pick up on by doing this sort of comparison between r theta space and xy space, and the reflections from the symmetries give it to you. So to wrap this up, this is a actual graph of this, and it's called a cardioid. So our r equals 1 minus cosine of theta as a polar graph is depicted here. It's called a cardioid because it looks like a heart. So this is a classic example of a polar graph, And this is also a classical approach, this idea of using the graph of the polar equation thought of as Cartesian to tell you the story of what's happening when you interpret them as polar coordinates in the xy plane. A very common technique, one that I highly recommend using. And we will explore some more examples in some other lectures.